let's just have a little summary about the case nearest neighbor algorithm, which we'll actually discuss in the following lesson with Python. And this is used in both user and item-based recommendation systems. And it is really simple. And all you do is you calculate all the distances between, in this case, this is user-based collaborative filtering between users and Alice. And then you identify those users which are near Alice. And if you have K of 3, you identify the 3 users that are nearest Alice. And if K is 20, you identify the 20 users that are near Alice. And then you use some formula to take those 3 to 20 users, or it could, of course, be bigger, and use that to help Alice predict what she'd like. And the algorithm is very simple. You calculate the distances, you sort the distances, and you take the K distances which are smallest. And that is, as it says here, is given in Python in the next lesson. We've already pointed out the sort of quite interesting issues about spaces. Users, of course, live in a space of items with rankings as coefficients. Items live in a space of users with the same rankings as coefficients. Those are sort of dual to each other. Or we can do the property or content-based approach where items live in the space defined by their content, which is the semantic information like in the music genome, or the words as they, if you look at these items, are documents. And then we can do methods like clustering, which we will discuss later, latent factors or mixtures of topics, which also identify things which are near each other. Those are the type of algorithms that are used by news-based websites like Google News, which are trying to find items, news items which are near each other. Here we have a little discussion about what it takes to find nearest neighbors. We have probably a pretty inefficient Python code later on, so let's not actually do that. We'll illustrate it for the user-based case. And if we have M customers, and we obviously have all the M distances to calculate, and then we want to find, if we're looking at Alice, we need to find the users which have rated enough items in common, and we have to sort those distances, and that takes a time order M log N. And so if K is very small, you will find it takes a time like K times the number of customers that have rated enough items in common. And this points out that the number of customers which rated items in common with Alice is actually pretty small compared to, incredibly small compared to the total number of customers. So you would never use the trivial algorithm, because you can always speed it up by using the sparsity of the system. Also, here's some little trivial examples taken from Wikipedia of K nearest neighbor classification. And we're trying to classify the green circle, and we have 2 categories to find: a blue category of squares and a red category of triangles. And this is not a very, this particular example is not very precise. If I take K of 3, which is the points in the solid circle here, that's 3 points, and then we might just do a voting algorithm, and notice of those 3 points, 2 of them are red and 1 is blue, so we will classify the green point as red, which is probably by eye the best classification. On the other hand, if we'd actually taken K of 5, which is the points inside this dashed circle, we would actually find 3 blues and 2 reds. if we just take a voting algorithm, which is just count the number of neighbors that have a certain classification, then blue would do better. If we did some averaging, which took account these distances, then actually you might still choose red, because the 2 reds are much nearer than the 3 blues. So these are all illustrations of these heuristic algorithms, where there are many ways of approaching it, and you can't actually guarantee to. There's no right answer. You just hope that you get pretty good answers most of the time. Here's a little comment about the so-called curse of dimensionality. If your points are in a very low dimension, it is very, very fast to find the nearest neighbors. What you can do is divide the points into a grid, assign the points to the cells of the grid, and then you can do that in a non-uniform fashion. Here's an example of a grid where there's a mesh, and maybe because lots of points are near one region, you have more mesh points here, but everything is still lots of cells. Then if I want to find the nearest neighbor to, say, a point who's in this cell here, I only have to look within this cell and maybe the neighboring cells. So this drastically decreases the computation time, because I do not have to loop over all items, or points I should say more precisely. Rather, I just have to loop over items in cells near the point I'm interested in. So this type of algorithm, however, only works in low dimensions. If you have high dimensions, you can easily see that it's not feasible to divide them into cells, because you want a reasonable number of cells. If you have a dimension of 1,000, which is actually far smaller than the typical dimension we're dealing with, which is measured in millions or tens of millions, or maybe now hundreds of millions, then if you divided each dimension into 2, then you would have a number of cells equal to 2 to the dimension, and that's obviously enormous. So this is a well-known feature about high dimension spaces, and some of the algorithms which are very effective in low dimensions don't work, so we can't do that method. Here's some example of something which is sort of illustrates maybe both the positives and negatives of this type of approach. This actually is a 2-dimensional projection of a 3-dimensional space, and these points happen to be genome sequences. And you can see actually they do fall quite nicely into cells. And if I want to find sequences that are near each other, I just go to the cells. I want to find sequences near this sequence here, then I just go to this cell, maybe this cell, and maybe that cell. That's it. That's all I need. Very efficient. Now, I just note that this is actually quite time-consuming, because these sequences actually live originally in a space of around 1,000 dimensions, and I had to use a technology called multi-dimensional scaling to map the sequences into 3 dimensions. And when in 3 dimensions, I could very efficiently apply this nearest neighbor algorithm. I don't think in practice this method of mapping into 2 or 3 dimensions to apply nearest neighbor methods is typically used, although in principle it could, is because that mapping is itself an computationally intensive problem, though it is one of these model-based approaches, so it's one you would apply in batch mode and reuse, because you can do it once and then interpolate it as data comes in, and you do not have to redo it every time you get a new data point. So this is lots of rich technologies, lots of remarkable features coming from lots of data in very high dimensional spaces, and this is really exciting how much we can get from this type of data that never existed. We never had data where components were rankings in the past. We always had different types of data where the components had a more solid physical meaning. Thank you very much.